Okay, you little chemistry whiners, right? You're here with me. Thank you for taking the time out of your packed afternoon to make sure you come in to class tomorrow with the right kinds of notes and hopefully a few more steps in the right direction to help you wrap your mind around reaction rates, all right? So what we're going to be looking at in our intro to reaction rates is the rates of appearance and disappearance, right? Appearance would be our products, of course, and as those products appear, we should see an associated disappearance of our reactants. Because, of course, those reactants are becoming the products, right? All right, now, we're going to do things slightly differently this time in that I would like for you to also have in your possession ChemQuest 42, all right? And part of the reason for that is I'm trying to value your time a little bit. So we're actually going to work through some of the questions from the ChemQuest, right? Stuff to do anyways, and that way we kind of learn in context. So definitely still have your notebook available, but also ChemQuest number 42. All right, so if you need to pause for a moment and grab those items, please get them and then come back and rejoin me. All right, so in your notebook, I would like for you to write some formulas down, all right? So as you guys know, and we talked about it in class, a rate is the speed at which something occurs, right? So it's a change in a variable over a change in time. So a reaction rate, right? We're looking at the rate at which the concentration of a solution changes. All right? And that's why we spent a few days on molarity or molality, right? So we're looking at the change in molarity, typically, divided by the amount of time required for that change in molarity. I hate that bell. All right. So moving forward. So formula, right? So the way we are going to measure our rate, we're going to look at the change in concentration, which is that molarity value, divided by change in time. So that little triangle, as you guys should have noted on your ChemQuest, refers to change in. Okay? In order to get the change in molarity, at least for the data, the types of data you are given in this ChemQuest, right, we have to remember that molarity is moles of solute per liter of solution. All right, so we're going to have to take into account both the moles and liters. So there's lots of units coming in here. So again, I'm going to remind you guys to label your numbers with units, and the better you are at labeling them, the better you can keep track of what your numbers actually mean, because they don't mean a darn thing if there is not a unit attached to them. All right? So, in order to find our change in molarity, we need to find out how much the moles of our solute changes, right? And the way we calculate that is the ending moles minus beginning moles. And I will put those numbers into context for you shortly, okay, as we go through some of the questions from the ChemQuest. All right? So, the way we get the change in concentration then, so that's this top number that we're looking at right here, okay? We're talking molarity at this point. In order to get that number, I have to take my change in moles divided by my total volume of the solution. All right. So in a question, like you'll see on your ChemQuest, on your tests and quizzes, you may be given data in terms of moles, but you'll also be told the total volume of the solution as well. Okay? And so the way we do that, so if the change in moles is the ending moles minus beginning moles, the change in molarity would be ending moles per liter of solution minus beginning moles per liter of solution. Okay, so sometimes you'll have more than a liter, sometimes you'll have less, and so we do need to indicate that number in the denominator. All right, and thing to remember here, so our change for our reactants should be a negative number. So reactants should end up with a negative number because we are decreasing our concentration, and our products should end up with a positive number because our products should be increasing their concentration throughout the reaction. Okay? So that's a lot of information. This is stuff that I would like for you to have in your notebook, right? And so we can refer back to that as we actually work through what these types of questions will look like on a test or quiz. All right. So this is what you see on page 2 of your ChemQuest. And so we're going to work through numbers 7 through 10 together. All right. So this is just putting things in context. So you can shift your attention over to page 2 of ChemQuest, and we shall see what is going on with all these numbers. Okay, so first and foremost, it looks like we're starting with a balanced molecular equation. All right, and that is going to be put on every single page because that is going to be really important to us, particularly these coefficients, 2 to 4 to 1. So we're still in this mole ratio mode. All right, now let's look at our table. So here's our column for time, and we are going to pretend that sig figs are not determined by that time value. So let's just put a 0.0 at the end of each of those just for good measure, right? Because I don't want to only have one sig fig. That's why I'm saying that. All right. Anyway, so that's our value for time. Now this is our moles of dinitrogen pentoxide. All right, and that is our reactant. And we should notice that these values are decreasing as we go down, right? And then over here, moles of nitrogen dioxide and oxygen gas, we should see those values increasing as we go down the table. All right, because those are products. All right. So number 7, it says calculate the change in moles of each reactant between 600 and 1200 seconds. All right, so we're going to be looking at these values for each of our steps here, okay? And so all we're doing is we're calculating a change in moles. So this value is already in moles. So all we're going to do is a simple subtraction problem, right? So change in moles of N2O5 will be simply done by taking 0.4104, whoops, that's a minus 0.4194. And that should give me a negative 0.0090. Okay, so again, ending moles minus beginning moles. And so in this time interval, 600 to 1200, this is my end, this is my beginning, right? So I'm taking this value minus that value. All right, same thing goes for change in moles of NO2. It's going to be ending minus beginning, so 0.0432 minus 0.0252, and I should get a value of 0.0180. Now notice N2O5 is a reactant, so that value is negative, right? NO2 is a product, so we should get a positive number. All right, and last but not least, oxygen here. I've got 0.0108 minus 0.0063, and that should give me a value of 0.0144. Sorry. That is not right. That should give me a value of 0.0045. Looking at the wrong number there. My apologies. Right. So again, let's make sure we're paying close attention to what's happening. These values are written in moles for me. I'm trying to find the change in moles. So I'm going to take my two values and subtract, right? My reactant, which is this number right here, notice it is a negative because my reactant should be decreasing over time, whereas these values are positive because they are products and their values should be increasing. So change in moles is just the ending minus the beginning. Fairly simple. All right? Now, let's move forward. Okay, now it says to compare the values from number 7 to the coefficients in the reaction, right? So again, remember I said we're going to pay attention to this mole ratio here? All right, so that's a 1, I suppose. 1 there, I don't want to confuse you guys. All right, so let's look at these values. N2O5, all right, its coefficient is 2. The NO2's coefficient is 4, and the oxygen's coefficient is 1. All right. So what we ought to see is that same ratio appear in our change in moles, right? So again, the nitrogen dioxide should appear at a rate 4 times faster, right, than our oxygen. Okay, so let's compare our nitrogen dioxide to oxygen. So if I were to take 0.0045 times 4, I should get 0.0180. All right. If I were to multiply that value then by 2, I should get 0.0090. All right. So what you need to think about and pay close attention to is the fact that those values, right, these guys, that change should mirror the same rate shown in our mole ratio, okay? So again, oxygen has a coefficient of 1, nitrogen dioxide has a coefficient of 4, right? So we should expect the nitrogen dioxide change, right, should be 4 times faster than the change in oxygen gas. Okay? That's what we need to understand. That's a triangle, it's just really sloppy. Okay. Moving on, number 9. We're going to fill in the missing spaces on this table. So we need to find this value, and we need to find that value. All right? So, first of all, with this type of question, right, one column is going to be all the way completed for you, because what we need to do, right, is, again, we're going to find the difference, the change that happens there, and then figure out what that looks like in terms of our mole ratio to find the values that exist for the other two parts of this reaction. All right? So the missing spaces are going to be determined by the change that happens between 1200 and 1800 seconds, right? And so the values that we need to pay attention to are these two guys right here, right? So we have a value that we can calculate between 1200 and 18 seconds for oxygen, and then we can use what we know about mole ratios to figure out what the change should be for nitrogen dioxide and dinitrogen pentoxide, okay? So, I'm going to do a quick math. The difference between those two values right there is equal to 0.0036. Okay, so that means my number of moles of oxygen increased by 0.0036. Now, the logic we need to apply to figure out this value right here. So first of all, nitrogen dioxide is a product, so it's going to also increase. Okay, but it's going to increase by 4 times as much as the oxygen increase because we have that coefficient of 4. So that means for every 1 mole of oxygen we should get 4 moles of nitrogen dioxide produced. All right. So in order to figure out this number right here, I need to know how much it should increase by. Okay. So this was an increase of 0.0036, right? So, therefore, I need to find, so my change in O2 times 4 would be equal to my change in NO2. This value, so 0.0036 times 4 equals 0.0144. All right, so that means my NO2 is going to change by 0.0144. So I'm just going to then add 0.0144 to that value, and I should get 0.0576 when I do that addition problem. Okay? Now, I know this seems like lots of numbers, but this is where thinking it through. Oxygen changes. The change in my oxygen is a positive 0.0036. All right? And that's just a simple subtraction between those two numbers. All right? According to my balanced reaction, my nitrogen dioxide should change by 4 times as much. So I took my 0.0036, multiplied it by 4 to get that number. That is the change in my nitrogen dioxide. So the change is a positive 0.0144. So I'm going to add 0.0144 to the previous value, and I should get 0.0576 as a result. All right. Same logic applies to my dinitrogen pentoxide, although it's going to change. So my change in O2 times 2 would be equal to a negative value for my change in N2O5. And that negative, again, comes from the fact that I am remembering that N2O5 is a reactant, and it will therefore decrease, not increase. All right? So this change here should be double that, but negative, so that should be negative 0.0072. Okay? And when I do that, I should get a value of 0.4032 as a result. So notice that number decreased, okay, by double the amount that this number increased over here. All right? So think it through. What does a change in something mean? It's a change in value. You find a change in value by subtracting. All right? If it's a product, it should be increasing by a proportion of that change. If it's a reactant, it should be decreasing by that same proportion. Okay? This is our first time through, but we should be getting this. Now, the crux of this, what we're trying to get to, is a rate of disappearance. Okay? Or a rate of appearance. So that's how we're measuring, is a rate. So going back to your notes, right? Our rate is going to be the change in molarity divided by the change in time. Okay? So change in molarity over change in time. And remembering that molarity is moles over liters. Okay? So my values are given to me in moles. Right? Now, on question number questions 7 through 10, it tells us, right, that we have a volume of 3 liters. All right? So this number, the 0.4320, for example, is not my molarity. It's the number of moles. All right? But that's dissolved into 3 liters. Okay? So what we have to do is I need to take that number, 0.4320, divided by 3 liters in order to actually understand or actually have the value for molarity. Does that make sense? So change in molarity over change in time. So the way I am going to calculate this, okay, is I'm going to take my change in moles over liters times change in time. That's the way I'm going to set this equation up. So for rate of disappearance or rate of appearance, same formula, change in moles divided by liters times change in time. So let's show what that looks like. We want to know between 0 and 600 seconds. So we're looking at those two values right there. So I'm going to take my end minus beginning, so 0.4194 minus 0.4320 divided by 3.0 liters times, that's 600 seconds. Okay, so I should get that number divided by 3 divided by 600. And when I do so 49194 minus 0.4320 equals, divided by 3 divided by 600. I should get a negative, again, negative because it's reactant, 7.0 times 10 to the negative 6 molarity per second. Okay, is the way that should look. And that's how I would do that. All right. Now, this is getting really long, so I'm going to stop here and let you guys tackle it from there on out. Hopefully, this will help you get started.